Allora.
Perfetto.
Okay, so it's a pleasure to be here to talk about some topics on rationality of varieties. Let me just mention that rationality is a very rich subject. I'm going to only touch two specific topics. And we're going to dig into these topics, especially in the first one, and use it as an opportunity to learn some techniques in high dimensional geometry that could be useful also for other problems. So today I want to motivate the first topic is birational rigidity. I'm going to motivate it starting from the Lueroth problem. So first of all, let me maybe just recall what a definition here. So actually, before I do that, let me just say that we're going to work over the complex numbers. There will be a next lecture we actually depart from this, but otherwise we're going to just stick with the complex numbers. Some results are more general, but in some places I do need characteristic 0 and algebraically closed. So might as well just walk over C. So if I don't say anything, think about that everything is defined over the complex numbers. And so let me just recall, you suppose X is an algebraic variety. So we say that it's rational if X is birational to a projective space. And we say, which is the same thing as saying that, let me write it here. If you look at the field of rational functions on X, it's isomorphic to, let me maybe start from 0. No, sorry, what do I do? What am I doing? It's correct, it's from 1 to n. And then we say that X is unirational if there exists a dominant map rational map from Pn to X. N could be the dimension of X, or it could be larger, it doesn't matter, I can always cut down to the dimension. And if you think about it in terms of field, you just say that the field of rational functions on X has an extension, which is pure transcendental. So the way you want to think about this is a variety is rational, unirational, if it admits a global system of coordinates defined almost everywhere. And the rationality means that this coordinate system is actually really one-to-one. So it characterizes point, every point has a unique coordinate. I mean, any coordinate determines whatever. Whereas unirational, you may have different coordinates given the same point. Okay, so Lueroth's theorem is traced 150 years ago about. It says the following thing. Suppose that you have a field K, for instance, the complex numbers, and then you have an extension, capital K, and when this sits inside little k with a pure transcendental extension, Kx. So this implies that the field in the middle is actually, so this is field extensions. The field in the middle is actually also generated by a single element of, sorry, I fix this. This is small k here. For some y's in it. So how do you think about this geometrically? Again, you think about, for instance, take k to be the complex numbers. And what you say is that if I have a map, so when you look at geometrically, having a field extension, it corresponds to have a dominant map between varieties. So what we're saying here is that if capital K has a is a field that is a field of a curve, then this curve is dominated by P1. So it's unirational. So what this says is that P1 is the only unirational curve, smooth projective curve. And the point is that you can actually understand this very quickly geometrically. Of course, this can be proved directly using field theory, but geometrically, what you want to think about is that what does it mean to be unirational? It means that there is some projective space P1, which is a dominant map, which in this case is a morphism between smooth curves, has to be a morphism, to X, to some curve X of genus G. And so this map is a covering map, it's an algebraic map, so it can only be ramified at finitely many points. And if you just compare all the characteristics, so it becomes really a topological statement of a C at least. So this implies that G has to be equal to 0. You can use Hurwitz formula, differential forms. You can look at this in many ways. And so this theorem and the geometric interpretation of this theorem has motivated, has led to a problem, which is known as the Lueroth problem. So, and this is in any dimension. Does unirationality implies rationality? Of course, that would be very interesting because it is in general easier to prove that a variety is unirational than proving that the variety is rational. There are many geometric constructions which provide this parametrization of the points on the variety, but this parametrization by the construction is often many times to 1. And whereas proving rationality directly is in general very hard. Can be very hard. So this is a problem. And so what do we know about this problem? So let's start, well, dimension 1 case, that's the Lueroth theorem. So the answer is yes. So how about in dimension 2? So think about now smooth projective surfaces. And the answer is yes by Castelnuovo theorem. Rationality. Okay, so what does it say? It says that if you look at, if you look at Q, which is, so let me actually write it this way. It's H1 over OX, or you can think about this as being H0 of omega X. So maybe I should say, suppose you start with X, so a smooth projective surface. Then you say it's rational if and only if Q equal to P2 is equal to 0, where Q is an irregularity, which is defined here, and P2 is a second plurigenus, which is H0 of omega X tensor itself. So dimension 2, again, you have a characterization of rationality by some vanishing in cohomology related to differential forms, like we have on curves. And so now let's check that we have a positive answer to the Lueroth problem. So assume X is unirational. So what do we have? We have a map from P2, some dominant map, to X. So what they're going to do is they take a resolution of this map. So now I get a nice morphism, F, where Y is a rational surface, smooth. And F is some generically finite map. So because X is smooth, when I put back shift differential on X, this maps inside differentials on Y. So now this implies that the regularity of X is bounded above by the regularity of Y, which is 0. And P2 of X is bounded by P2 of Y, which is also 0. So this implies that X is rational. Okay, so this settled the problem in dimension 2. And now the question is what happened in higher dimensions. So this problem was open for many years. And then finally, it was shown that in high dimension, greater than 3, the answer is no. So, and this was proved independently by 3 teams of mathematicians in the early 70s. So the first team is Skorsky and Manning. So what Skorsky Manning shows is that if you look at smooth quartic threefolds, upper surfaces in P4 are non-rational. And then there is a theorem by Clements and Griffiths. We say that if you look at smooth cubic in P4, so in threefolds, these are also non-rational. And then shortly afterwards, a third result came out by Artin and Manford. Which they construct examples of conic bundles on surfaces that are unirational, but not rational. So each of these theorems leads to a counterexample. The Lueroth problem. Maybe I should comment that I think the third case is clear because in the proof they actually show that this example are unirational and not rational. In the first two, so why do we know that? Well, in the case of in the Clements and Griffith situation, so if you have a cubic in P4, what you can do is that you can take 2 upper section and you got a surface here, S1, and then you get another upper section, you got another surface, S2. Maybe the 2 is down here. So this surface is rational. So what you do is that now you're going to take, for each pair of points from the 2 surfaces, you take the lines to these 2 points, and generically you expect to have a third intersection point. So the third intersection point defines a map from S1 cross S2 to X, which is dominant, and X1 and X2, of course, is birational to P4. Okay, so you get this unirational parameterization. And in the case of Skorsky-Manning, well, it's a bit more complicated because it's not known in general. I think it's expected it's not true that all smooth quartic threefolds are unirational, but there are examples. Of unirational quartic. threefolds due to Segre. So those examples were already known, and therefore let's also give a counterexample. Okay, so we have this theorem here, which settled this problem. So it's not true in general that rationality. So we have rationality. This implies a unirationality in an obvious way, but the converse is false in general. So there is a related problem that I just mentioned here that is still open instead. Unirationality implies rational connectedness. Let's say a smooth projective variety. And the question whether the converse holds is actually open. So that's one of the big problems in this area that has been open for many years. I think the answer is certainly expected to be negative. In fact, probably already is possibly even quartic threefolds might be a counterexample to that. But we don't know that. Okay, so what do we have? We have these three theorems in dimension 3. Again, came up at around the same time. They give the same type of counterexample, but they deal with different type of threefolds. The quartic threefolds, the cubic threefolds, and conic bundles. So what is interesting here is that there are 3 different proofs. So the idea is that how you prove something like this, how you prove that something is not rational. In principle, you would like to say that you cannot construct a rational map, but that seems hard because you have infinitely many degrees and equations to check. So it seems impossible to do that. So instead, what you typically do is that you look for a birational invariant to distinguish X from a projective space in a birational sense. So if I can give you a birational invariant, I compute this birational invariant for the given threefold, say, and then or variety in general, and then I show that this birational invariance doesn't match the birational invariance of the projective space, then I conclude that the variety cannot be birational to the projective space. In particular, it's not rational. So let's just maybe mention that in the 3 theorems, they looked at 3 different birational invariants. So in the theorem Minkowski-Manning on quartic threefolds, they look at the group of birational automorphisms. It's certainly a birational invariant, if you like, it's isomorphisms, automorphism of the function field of the ground field. The second is they look at Clements and Griffiths look at intermediate Jacobian. And the last one, maybe I should say modulo Jacobians of curves. The intermediate Jacobian itself, think about, is not really a birational invariant, because if I blow up, maybe I blow up a curve on a threefold, that Jacobian will change. But what you show is that it changes because the fibers are projective spaces, it will change by the Jacobian of the curve I'm blowing up. So if I mod out by Jacobian of curves, so I kill all the factors appearing in the composition of the Jacobian that looks like Jacobian of curves, then whatever is left is a birational invariant. And the last in Arten and Manford, they look at the Brouwer group. Okay, so each of these methods has its own features, has its own benefits, and its own limitations. And so when I look at those three examples in the three theorems, I cannot use different methods. I cannot combine the method differently with examples. So here in these lectures, I will focus on the Minkowski-Manning theorem, which says that if I look at a smooth quartic in P4, it's not rational. Okay, so that will be the focus of our first 5 lectures, in fact. So I want to spend the rest of this lecture to actually, so maybe just mention here, so this fact, the fact that the quartic threefolds are not rational, this was first claimed by Fano. So Fano had already a good strategy to prove that the birational group transformations. So Fano's claim, in fact, if I look at the group of birational transformations, so these are the map from X to X, which are birational. So they're not defined everywhere. They're rational maps from X to X, but they have an inverse, a rational inverse. So this, of course, contains a group of automorphisms, which are regular automorphisms, so X. And Fano claims that these two, in fact, are equal. And I claim that this already is enough to conclude that X cannot be rational, because the group of automorphism of a quartic threefold is finite, but the group of birational transformation, a common group of P3, is infinite. It's very large, in fact. So it cannot be the same. So the inspiration in Fano approach, it comes from Noether's factorization theorem. Okay. So I want to focus on this today. This is not strictly speaking, related to a problem of rationality, but there is something in the proof which is then was taken again by Fano and other people, and eventually led to the proof of Minkowski-Manning theorem. So let's try to see that. So the next thing I want to talk about is factorization planar Cremona maps. So maybe I should say, so here we look at the Cremona in dimension 2, the Cremona group. This is a group of birational transformation of P2. So this is a group of math from P2 to P2, which are birational. It's called the Cremona group. So the theorem is due to Noether and Castelnuovo. It says that this Cremona group, the birational group of P2, is generated by linear automorphism and the standard Cremona transformation. Chi, we go so from P2 to P2. So P2, I think about your fixed coordinates. And in these coordinates, this transformation is given by taking a point x, y, z and mapping to the point given by y, z, x, z, x, y. So this is not defined everywhere. For instance, at the point 1, 0, at the coordinate points, 1, 0, 0, 0, 1, 0, 0, 0, 1, I'm going to get 0, 0, 0, which is not a point in the projective space. So the way you understand this is that you, oops, what happened here? You have this coordinate give a frame in a projective space. When you have, let me use the same order here. So this is point 1, 0, 0, this is point 0, 0, 1, and the point 0, 1, 0 is up here, these 3 points here. I'm going to write the other copy of P2 upside down. So what happened here is that the first thing you do is you blow up 3 points. So when you blow up these 3 points, it separates the coordinate axis. And the section divisor intersect the axis in this way for kind of an hexagon. So the section divisor comes from these 3 points that we blow up. And then what we're going to do is that you go down this way and we contract. Let me actually, sorry. Right. And then we contract 3 axes. So the white axis, the proper transform of the line, so the points, so pair of points. So when we contract, for instance, this axis here, it will go down to this point. This axis here will go down to this point. And this axis here will go down to this point. Okay, so of course, there are a lot more Cremona transformations. But the claim is that every time I give a Cremona transformation, I can write it out as a product, as I can factor as a composition of the Cremona transformation in a given system of coordinates and the linear transformations. Now, the role of linear transformations is to move those coordinates around. So another way of thinking about this is that instead of looking at linear transformation, I can absorb them in a choice of coordinates every time. So I can just talk about standard Cremona transformation centered at triples of points around the plane. And I apply one and I change coordinates and I apply it again and change coordinates. So the change of coordinates plays a role of the linear transformation. So and that's what I'm gonna do. So what is the idea? The idea of the proof. Is the statement clear? So by the way, I should say, if you feel free to ask questions at any time. Okay, so you start with an element in here. I want to factor this into product or those more elementary transformations. So what is this? C is a Barashian transformation from P2 to P2. So this is given by some linear system H of given some degree. So the equations will be the equation of given some degree, and I call the degree R. So I look at OP2 of R, look at the complete linear system, and I just pick a dimension 3 subsystem. A two-dimensional, so, yeah, two-dimensional linear subsystem. So the way you want to think about this is that H is the inverse image of the complete linear system on the other copy of P2 given the coordinates from the other side. So this is what it means to give an equation of a rational map. Yes, there's a question?
Yes, I don't understand your last notation, 5 star minus 1.
Yeah, so this notation, I don't know how standard it is. I think people call this a homoloidal transformation. So what it is simply a linear system. Let me just show you in this example here. So this, you think about these three forms, these are degree 2 forms. So those degree 2 forms, they generate a subsystem in the system of conics on P2.
Mm-hmm.
So the way you want to think about this is that you have coordinate x, y, and z here, and maybe on this side you coordinate u, v, and w. So in this here, this is u, this is v, and this is w. So when I write them u, v, w, I'm thinking about just linear coordinates on this side of the map. And just to give a map, I just need to tell you where this coordinate goes on the other side. Remember that algebraically the map goes the other way. And so I just say that u is equal to yz. So the element, the divisor defined by u equal to 0 will define an element in here defined by yz equal to 0. So r is equal to 2 in this example, and so on. Does it make sense? Another way of thinking about another thing of thinking about geometrically is that you start with a divisor here, you pull it up. So when you pull it up, you're gonna get something like this, and then you push forward. And when you push forward, this guy gets killed, but these two survive, and then you get something like this.
Mm.
But you can also take maybe a general line. A general line passes this way. When you let me do this in actually. If I take a general line this way, so this goes to the two yellows. So it goes like this. And when I contract the two yellows, it's gonna pass through 2 points, but it's different from one. So it's gonna become a conic. They're gonna go around this way. So that conic is an element of H. So in this case, for this example, H is exactly the system of conics in P2 which pass through the 3 points. And if you just count dimension, I think the space of conics was 5 dimensions, something like that. You put 3 conditions, I cut it down to 2 dimensions.
Mm. Yes, now it makes all sense. Okay.
Very good. I'm glad. Good question. Anyway, everybody, feel free to ask questions. I think it's good to explain these things.
Tommaso?
Yes.
How do you pick R? Z number is, you fix it?
So the way you pick R is exactly by this construction. You take a general line on the right-hand side. You pull it up, and then you push forward.
Okay.
There will be a curve in P2, and the degree of the curve is R.
Okay.
Another way of saying this is that you just write the equations like it's written above. After you do all those simplifications, because these are homogeneous coordinates, you're left with a homogeneous system, with an equation which are given by forms of the same degree. That degree is R.
Okay, thanks.
Okay. In fact, one thing you notice here, there was my next comment, is that let me assume the phi is not an isomorphism. Otherwise, there's nothing to prove, right? We already know isomorphism are linear transformations. So this means, i.e., R is greater than 2. If R is equal to 1, then it's elementary to see that there's no other options here. It has to be an isomorphism. Okay. So now what you do is that you take a resolution, you take a minimum resolution. So the way I do this resolution, I want to take a resolution from Y to P2, and I'm gonna write this as a composition of blow-ups. So this P2 will be some x0, and then will be the first blow-up, F1, x1, all the way to some xk, and xk plus 1, and fk will be the last blow-up. So that when I look at the rational map phi, after taking this resolution, become a well-defined morphism. So each fi is a blow-up of a point mi, oh sorry, pi on the previous model on xi. So xi blowing up p0 is here, then I blow up p1, which is here, and so on. So that's just take the minimal number of blow-ups to allow this. So every time you blow up, you have a linear system because you have a rational map going down this way. So you still have a linear system, hi, linear system on the model xi, and I'm going to denote by mi the multiplicity of the linear system, which means the multiplicity of general element of the linear system at a given point pi. I can assume, because if I blow up over the same point, the multiplicity cannot go up, it can only go down, because by blowing up, I cannot resolving partially at least the linear system. So I can assume the channel multiplicity is decreasing, is not increasing. There's the last one, and the last one will be positive because assuming this is a minimal resolution. Okay, so I have this point, I have the point P0, P1, all the way to Pk, have k points, and which form a kind of a base locus of the linear system in some sense, and then I define these numbers, which are the multiplicity of the linear system at these points. I need to do this one at a time as I take these blow-ups. Okay. So what is Noether idea? So you want to apply, by moving the coordinates around, you want to apply the standard Kermano transformation centered at the first 3 points. These are the points of maximum multiplicity, or largest multiplicity. 1, P2, to lower the degree of phi r. Okay, if I can show that by applying a standard Kermano transformation, quadratic transformation, I lower the degree of the equation of the map, what happens is that the degree is an integer, so it goes down. It can only go down finitely many times. So after 5 many steps of repeating this idea, I would come to a linear transformation. Linear transformation are all in the middle because I need to move the coordinates around to center chi at the 3 points. But I get a factorization of phi as a product of linear transformations and standard the quadratic transformation. So in order to show that this actually lowers the degree, Noether shows that this key inequality, which says that if I look at the multiplicity of the 3 points, if phi is not an isomorphism, then the multiplicity of the 3 points needs to be larger than the degree of the map. So this is the key inequality, and this is inspiration for what Fano wanted to do and tried to do, and eventually Skoski-Mani succeeded. Okay. So let me maybe explain a little bit about this. The setting is very different, so there are, of course, differences. It's just an inspiration for the work that came later. But let me prove this inequality. So remember that the linear system H, of which we are counting multiplicities, is this proper transform, or the transform, if you like, of the system of lines of P2. So if I pick a general element D inside here, this comes from a line in P2. And the line has 2 things. It's degree 1 and is rational. Okay, so this yields the following equations. The first equation, when you add on all multiplicity, mi squared, r squared minus 1, you get this inequality, and this comes from the fact that the degree is equal to 1. So it's the self-intersection of the curve, not on P2, but on the resolution of this y. It has degree 1 because it comes on line from a general line in P2. Another equation, and this comes from the fact that the curve is rational, is that if I look at the sum and the multiplicity without squares, this is 3. Did I write this correctly? Just a second. Double check. Yeah, I didn't. 3r minus 3. And this comes from the fact that these are rational curves. Okay. So now from this, I want to infer that we get that the 3 largest multiplicities satisfy this bound. Okay. So this is just a kind of a manipulation on the equations. I'm going to let A be the following number, r minus m0 divided by 2, and B is a maximum I such that mi is greater than a. Remember that mi is a monotone sequence of integer numbers, and okay. So now what I'm going to do is that first I'm going to take this equation, and I'm going to subtract 8 times this equation. So I'm going to do term by term, side by side. So what we get is that we get the sum. Okay, it goes from 0 to, sorry, this is not a k, it's an I goes from 0 to k of mi minus 1 minus a. That will be equal to what? When I subtract, put it together, this is r minus 1 times r minus 3a plus 1. So, yeah. And this is by combining those two equations. Now what I notice is that because this mi are greater than a only for up to b, and here I sum up from 0 to k and have this mi minus a. So some of these terms eventually will be non-negative, non-positive. So if I get rid of those terms, I get something which is not going to be smaller. So if I just restrict the sum on the first b terms, I get something greater or equal to whatever is on the left-hand side. And then I can in fact actually improve what is on the left-hand side by removing, so let me maybe do one step. If I remove this quantity, which is 3a minus 1, which is positive, it's not negative. So then this will become equal to r minus 3a, which is the same as r and 0 minus a. Okay, so you just need to play with the definition of a little bit to see these quantities. And this is just because m0 cannot be larger than r. There's a 1 here. Okay. Now what I'm going to do is that I look at the first term here when I is equal to 0, and I'm going to bring it to the other side. So here I get I goes from 1 to b, and I minus a, and this is greater or equal than what? R n0 minus a minus m0 times n0 minus a, which is the same thing as r minus m0 times n0 minus a. Okay, now the last step is to compare this to which one? To this guy. I want to compare. So the fact is that we have that, well, r minus m0 is equal to 2a, and this is by definition of a. On the other hand, we have that mi is less or equal than 2a for every I greater or equal than 1. And this is because n0 plus mi cannot exceed r. Because otherwise the lines through these 2 points will be intersect the general curve more than the degree of the curve, and it will contradict Bezout. So by that comparing this, then it means that this quantity here is less, this coefficient here is smaller than this coefficient. So if I eliminate this coefficient, I still maintain the inequality. So it follows that the sum of I goes from 1 to b and I minus a is greater or equal to m0 minus a. But m0, sorry, did I miss a strict inequality somewhere? Yes, I need to fix this. This guy is actually positive. So when I subtract something positive, I get a strict inequality here. So I have a strict inequality here and here. But m0 is greater or equal than all the mi for I greater or equal than 1. So in order for this inequality to hold, I need to have at least 2 terms in the sum. So this implies that b has to be at least 2. Remember that b wasn't, so it means that you have m0, m1, and m2, they're all greater than a. Sorry, m0, of course, we know. But remember also that m0 is equal to 2a minus r. Sorry, the other way around. R minus 2a. So what we get at the end, if I look at m0 plus m1 plus m2, I get where m0 is r minus 2a, but the other one I use an inequality, so this is greater than r minus 2a plus a, which is exactly equal to r. So this proves this inequality. Okay, so I hope that you're still with me. It's a bit kind of a long computation. But so what we did is that we proved this inequality. So I have these 3 points that in the base locus of the linear system with the largest multiplicity, and the sum of the multiplicity of these 3 points exceed the degree of r. Okay. So suppose you have 3 points, P0, P1, and P2 on the distinct points. On P2. You note they cannot be collinear. Because otherwise the lines of the 3 points are going to intersect the linear system in degree larger than the degree of the linear system, which is impossible by Bezout. So we're gonna look at phi composed to chi, where chi is a standard a quadratic transformation centered at these points. So what I do is that, again, I change the coordinates, so linear transformation, to bring those 3 points in the coordinate points, apply chi, and pre-compose to phi. And what happened there is that then you can check that, so you get a new transformation, phi prime, phi composed to chi, it goes from P2 to P2, and then you compute, it's a kind of a standard computation, I leave it to you to do. The degree of phi prime will be twice the degree of R minus M0 minus M1 minus M2. But then because of this inequality that we just proved, this will be less than R. So the way we want to think is that the chi untwists phi, lowering the degree. And after finitely many steps, we get to linear transformation. Okay, so we factor phi as a composition of linear transformations and standard quadratic transformation. Okay, so so why I'm claiming that this is not actually a proof. The computation is correct, the strategy is perfect, but there is one point where the proof breaks down. So there is an issue. The issue has to do with this assumption here. Here, I'm assuming that the 3 points are 3 points on the plane. But if you remember, we pick up these points on a sequence of blow-ups. So you first blow up P0 on P2. After the first blow-up, you blow up a point P1. And then after that blow-up, you blow up P2 and so on. But there is nothing telling us that maybe the point P1 was an exception divisor over P0. So if that's the case, then these points are not distinct on P2. They're infinitely near to each other in principle. So the issue here with these 3 points might not be distinct. They may be infinitely near points among them. Yeah. So if I have infinite near point, how do you get the red line there? I don't know. If I get these infinite near points, no, this is there. Oh well.
No, scusami, l'ho fatta io per sbaglio.
Oh, l'hai fatta tu? No, non ti preoccupare.
Non so come si cancella.
It's okay. I was just wondering what it was. Anyway, so there might be these infinite points among them. So we cannot apply chi directly. So what is the solution of this problem? Well, any questions so far? So what is the solution is that I'm gonna do this the same strategy, but I'm not gonna work always on P2. So you're gonna do the same steps, but on other, here's the Bruce surface. Okay, so if the points are infinitely near to each other and I try to apply the same strategy, I need to make these points distinct, and I can make this point distinct on some Hildebrand surface. So I have some sort of elementary transformation of P2. If I can do that, then I can try to repeat the same strategy. And this is what the way Casanova actually wrote the proof correctly. So here we're going to follow a slightly different, I mean, the proofs are, of course, are not very different from each other, but the way they're organized is different. So here I'm going to present this proof by Alexander. Which is only works on, it doesn't require us to move on different models. We can allow us to just work on P2. Of course, there is a catch for that. So the idea is that I want to do two steps here. So step one, I'm going to prove a weaker statement. The corona group of transformation of P2 is generated by linear transformation the standard Cremona transformation, which let me write it again. And then another transformation, I'm going to call it omega, is also quadratic, but it's not the standard one. So the equations of these are the following: x squared, xy, yz. And then the step two is so show by direct computation that omega cell factors as a product involving linear transformation and the standard quadratic transformation. So I first prove a weaker statement. We'll allow an additional generator in the picture, this non-standard quadratic transformation omega. And then I show that in fact I didn't add anything because this one is already in the subgroup generated by linear transformation in chi. So let's focus on step one. First of all, let's try to understand how omega looks like. So this transformation omega, maybe say note. Omega has 3 base points. I'm going to call it Q0, Q1, and Q2, where Q1 is infinitely near Q0, and Q2 is not on the line through Q0 with tangent direction Q1. So let me explain this. So again, look at the other, again, omega, let me write it one more time. So this also gives you this explanation also gives a sense of how you actually interpret these equations when you think about the linear system. So what I'm going to do is that, well, first of all, I see where indeterminacy point so the indeterminacy points are those points in x, y, and z which give the non-point 0, 0, 0 on the other side. Okay, this is where the map is not defined. So how do you get 0, 0, 0? Well, I could have x and y equal to 0. So I have the point 0, 0, 1. I could have x and z equal to 0. And so I give me point 0, 1, 0. And that's it, really. If you just think for a moment, these are the only indeterminacies of this map. So this is where the map omega is not defined. Okay, so now we can look in local coordinates. So maybe say in affine coordinates. Okay, so let's do that. So let's look in, we set z equal to 0. So we are looking at the XY chart, affine chart. So, and now I'm thinking about what happened to this. I have 3 sections of O2 given by x squared, xy, and yz, but I'm looking in the affine chart where I'm setting z equal to 0. So at the section of the linear system, the section of O2, determining the linear system, I give you the base locus of the linear system. So I see that the base ideal of H in this affine chart is given by x squared, xy, and y, which of course is the same thing as x squared and y as the ideal inside C, x and y, inside this polynomial ring. So in order to resolve the equations, I need to resolve this base scheme of the linear system. So I need to blow up this ideal. But you see, this is not just the maximum ideal. So the blow up of the point will not suffice. The way I want to think about this one is that I have in the coordinates, in this local chart, the coordinates x and y, I see that Q0 is this point here. I'm going to call it Q0. And then, but I also have a Q1, which comes from the x squared. So this moves in this direction. So it's a tangent vector here, the tangent direction, meaning it's a point on the first blow up. And that's how I think about Q1 as an infinite near point of Q0. If you put Q0 and Q1 together, and I can think of this as being the scheme defined by that ideal. Okay, so now I can do the same thing in the other point was the point 0, 1, 0. So for that one, I need to set y equal to 1. So now we are in the XZ chart. And now I look at the equation of the equations. So the base locus of the linear system will be defined by the ideal. When I set y equal to 0, I have x squared, x, and z, and that's the same thing as the maximum ideal, c, inside the polynomial ring. Sorry, inside here. Okay, so now in this chart, I have x and z, and I just have a point here, and that's my point Q2. So when I see, so globally, if I look on P2, I have, I'm going to do a similar picture that we did for the standard Kermano transformation. So we have a coordinate axis, and that's the point 1, 0, 0 here, the point 0, 0, 1 on this side, and this is the point 0, 1, 0. So what we have is that this point is in the base locus. This is Q0. This point is Q2. And then I have a Q1, which is a tangent direction in this direction. This is Q1. Okay. So what you notice here is that, yeah, so you show that in particular, Q2 is not on the line spanned by Q0 from Q1, from Q1 from Q0. So again, what I'm going to do is that I'm going to absorb the role of linear transformation with allowing myself to pick coordinates. So every time I see 3 points on the plane, where 2 points on the plane and one is an infinite near point, which is aiming in a direction away from the third point, then I can always fix coordinates so that the points look like these ones. And then I can apply omega there. So let me sketch the proof of step 1. Okay, so that the Gromov group is generated by linear transformation, chi and omega. Okay, so the strategy is the same as before. I'm gonna let R will be the degree of the map, which by definition is the degree of the linear system H. And then we have this minimal resolution. Of phi, which produces a bunch of points. The points are going up. So it's some P0, P1, all the way to some Pk. And then we're going to have multiplicity M0 greater than M1 greater than Mk, which is positive. And now we're going to set A, which is A of phi, as before, like the way we did before, is R minus M0, the larger multiplicity divided by 2. And B, which is also B depends on phi, which is a maximum index I, such that the multiplicity Mi is larger than A. And we know that this one is greater than 2. So the proof of the statement is okay. For that one, we don't really use that the points are distinct. So we have that, that property. So in particular, we know that M0 plus M1 plus M2 is larger than R. Okay. So now, so the plan here is to untwist phi by chi and omega in suitable coordinates. Okay, so again, the choice of coordinates absorbs the linear transformations. Okay, and show that somehow some degree goes down, but it's not going to be R. So that's the interesting part of this proof. So we use induction not on R, but rather on this pair of numbers A, B. And I think about these numbers are in this, where A is a half on a natural number. B is always a natural number. So I'm thinking about inside this group, 1/2 n cross n, with the lexicographic order. Okay, so I put the lexicographic order on this lattice, and I look at pairs AB in there, and I just do induction. So you notice that this is still a well-ordered set. Okay, so there are two cases. There's our plan. According to so now I need to look at these points. I need to be careful about the use, how to use these points. So there are two cases. So case one is that these points P0, P1, and P2 are distinct. So in this case, I'm just gonna let Phi prime to be the composition of the pre-composition of phi with the Cremot transformation, where here is this is the standard Cremot transformation centered. So centered. Oh, then I'm writing here. At these points, P0 again. These points cannot be collinear because the sum of the multiplicity is larger than the degree. So I can move these points into the coordinate points and apply chi first, and then apply phi. So we really know that the degree goes down, but that's not what I'm looking at now. So I need to be a little careful. I'm not doing induction on R anymore, because the case 2 will not actually work if I just look at R. Instead, I need to look at the pair AB. So, but still, we have computed that the degree R prime is 2R minus M0 minus M1 minus M2. When I look at these points, P0, P1, and P2, after I do transformation, they're gonna give me new points, which I'm gonna call, I mean, maybe I should explain this a little bit. Let's see. So the way you want to think about this composition is the following. So this is a map I start from. And here are the points Pi that I'm looking at with the multiplicity Mi. And the degree is R. Now what I'm going to do is I pre-compose with chi. Chi, I can go either way because chi is equal to its own inverse. So I'm not too worried about that. Sometimes I'm thinking about going the other way. So I can go this both ways. And now here I'm going to have a new degree R prime when I'm thinking about a composition map. And then I have some points Pi prime and some multiplicity Mi prime. In particular, I'm looking at the first 3 points. They get transformed in the coordinate are still the coordinate point, but I'm thinking about new points, and then multiplicity will change. Okay. So these are the points P0 prime, P1 prime, P2 prime, which is going to be in the base locus of the linear system H prime. They're going to be the first, no, I'm not saying they're going to be points I'm going to blow up to resolve phi prime. And then the multiplicity M0 prime, M1 prime, M2 prime. This is the multiplicity of the linear system H prime given the map phi prime. Okay, so another thing I can check by just looking at this Cremot transformation and what it does to the curves in the linear system H when I transform it to the other side by chi, is that I see that for every time I look at H, I, J being a permutation of 0, 1, 2, so I just look at these 3 multiplicities, I see that the multiplicity at point PH prime, which is NH prime, is going to be equal to R minus Mi minus Mj. Okay. So now I need to be a little careful here because at the beginning, I know that M0 and M1 and M2 were the largest multiplicities. But after I do this untwist, I have these new numbers, these new multiplicities. I no longer know that those are the largest ones. So the order might have shifted now. Maybe some other multiplicity might be larger. So now I need to ask, where is the largest multiplicity of H prime at? If it's not at the point P0 prime, then what we see is that if I look at 2A prime, that will be, I need to apply the previous inequality to the situation. So I'm going to have a strict inequality like this. But if you just look at the previous equations that we wrote above, you can compute that this is the same as R minus M0. And that we know is less than A, and less than 2A. Okay, so in this case, you see that the point A prime B prime in the lexicographic order is less than the point AB. Another case is that if it is at P0 prime, then it shows that A prime, that will be equal to R prime minus M0 prime divided by 2. And that will be the same as R minus M0 divided by 2 is equal to A. So that entry will not change, but you can check that B prime decreases. And this is because if you just look at the multiplicity of the other 2 points in this triple of points, Mi prime for I and J equal to 1 and 2, well, you can check that, well, this is equal to what? R minus M0 minus Mj. So it's 2A minus Mj, and this is less than A. So what it says is that before, when I was counting B, the point P1 and P2 were counting for B. You know, they were in, part of the indexes that they amount for B. But now that I am twisted, the point P1 prime and P2 prime, they no longer satisfy that inequality of the multiplicity. So therefore, B decreases by 2, in fact. So this implies that you still have that A prime and B prime as a pair in the lexicographic order is less than AB. Okay. So I promise that this is a most computational lecture. Actually, I realized it's more computation than I really meant. Other lecture will be a little more conceptual. So let me just mention something about the case 2 and then finish for today. The case 2, suppose that P0, P1, and P2 are not distinct. So there's an infinitely near points among them. So we follow a similar computation. What you do is you add an additional point, maybe an extra point, Q in P2 to be a general point. So in particular, it's not going to be on any interesting line that I have already on the point coming from the point PI's. So say for instance, P0 is here, maybe P1 is something like here. I don't know where P2 is. P2 might be on the same line or maybe not. But what I'm going to do is I'm going to put a point Q. And now I'm looking at, and I fix this coordinate. Okay. And now what I'm going to do is that I'm going to consider the triple P0, P1, and Q. Okay. So if P1 is not infinitely near P0, then I twist by chi, centralized points. If P1 is infinitely near P0, then untwist. Like in the picture that I draw above, then untwisted by omega. Either way, we get by a similar computation as before that this pair in order goes down. So after the final step, we reduce to the process must finish, must come to a term. So that is a sketch of the proof of the theorem. Again, it's a bit computational, but I think what you want to take away from this is the fact that you want to understand a birational map between two varieties. In this case, it's from P2 to P2. And what you do to understand this birational map is you look at the linear system or the equations of the map that define a linear system on the variety, and you look at the base locus. If there is no base locus, then it's a morphism, perhaps an isomorphism, and then there's nothing to do. But if there is a base locus, then you want to understand how singular this base locus must be. And this inequality of Noether arguments, that the sum of the multiplicity, this inequality here, is a key thing to focus on. So what it says here is that in some sense, the singularity of the linear system, if the linear system is singular, so it has a base locus, then it cannot be, the base locus itself must be quite singular, and is quantified in this way. So it relates the singularity of the linear system to the degree of the map. And so final idea was that we should be able to do the same thing on a quartic threefold. You have a map on the quartic threefold to itself. Suppose it's a birational isomorphism. Suppose it's not well defined, so it's not an isomorphism, regular. So it has a base locus. And then his claim is that this base locus has to be very singular. And then you want to use some Bezout argument to argue that it cannot happen because the singularities are too bad to be feasible. So we kind of use Bezout here already a few times. Of course, the situation of working on a quartic threefold is very different than working on a projective space or projective plane. You're not going to see appearing 3 points necessarily. It's going to be just 1 point. We're going to try to quantify the singularities of the linear system and show that that cannot be true, cannot happen. So that's the idea. Final argument. Yeah, say. Ask. Gilberto, yes.
Yes, in the last argument, when you say that the 3 points are not distinct, can all of them come together?
Yes, in principle, you could have P2 over P1 over P0. So that's certainly possible. So the idea here is that if these are not distinct, then I'm not going to actually use P2 at all. Okay. I'm going to use P0, P1, and this auxiliary point, Q. Because I want to make sure that the three of them, they have a configuration where I can either apply chi or apply omega. So I cannot allow, for instance, the 3 points to be on a line, so I need to be a little careful about the 3 points. Yeah. In any case, so what I'm going to do next time is slowly move towards understanding what we need to do to study the birational geometry of a quartic threefold. But in fact, there are some difficulties that we need to overcome before we can get to understand this, formalize this strategy in dimension 3. And the idea is that we're first going to actually still find a situation where we can apply these ideas in dimension 2. It seems hard to find another setting. I'm going to come back to this on Thursday. But there is actually a nice test ground to apply this technique in a situation which it cannot be seen simple in a sense as it is two-dimensional as working on P2. but at the same time is not on P2, is on something which is to be similar to the quartic 3/4. And I will tell you exactly what it is on Thursday. And then after that, then we're gonna move on and prove Minkowski theorem, mining theorem, and then discuss also how can we extend that proof to higher dimensions and what is the right setting to consider there. Okay, so this is it for today. Any other questions?
Yes, I am sorry.
Yeah, go ahead.
A lot of questions. But I was interested in this relation between the singularities of the base locus. How does it carry on to higher dimensional varieties? There are other tools or?
Yes, so this will be something we're going to spend quite a bit of time to understand. So
Okay.
on surfaces, as we're going to see next time, really what you need to do is understand what happens with multiplicity. So you're going to just use multiplicity as a measure of singularity. But in higher dimension, this is not adequate for this kind of problems. It's insufficient. So we're going to use a more sophisticated way of measuring singularities of linear systems.
Oh, cool.
Yeah.
Bene. Grazie.
Are there other questions? Okay, so Flaminio, what should we do? Should we just stop? We're going to resume on Thursday.
Sì. Perfetto.
Okay, very good.
So we're gonna meet at the same time next in 2 days.
Ok.
Non vedo più nessuno.
No, come nessuno? Ah.
No, non